Greetings. This is a presentation of the paper with paper ID 1515 titled Ergonomic Knee Exoskeleton System with Real-World Perception and Actuation using Computer Vision, Image Processing, and LiDAR Data Fusion. The authors are Vinod Vasan, that is myself, the presenter, and Dr. Abhishek Rudra. Knee joints are indeed important biological provisions since they act as weight-bearing agents, attribute locomotive stability, and promote great flexibility over a wide range of motion. So it is indeed obvious that any form of damage to these provisions would negatively affect the regular operations of an individual and in the process inflict great pain. At the same time, individuals with visual and mobility impairments, skeletal strain, permanent muscular damages, and those recovering from plausible surgeries, which were, after all, aimed at resolving these aforementioned ailments, can possibly benefit from a mechanism or mechanisms to at least experience a temporary respite in the front of general mobility. Therefore, this study, in view of the aforementioned causes, proposes a design and implements the same via a prototype, which is centered around a robust computational framework coupled with a dedicated computer and actuation system, acting as a surrogate for visual perception and actuation. Prioritizing user comfort, the ease of implementation, with a focus and through an approach of camera LiDAR data fusion for the purposes of improved societal integration and user independence is one of the key strategies that we are examining in the study. The proposed system achieves the end goals of a contemporary knee exoskeletal system with twice the functionality, but at a fraction of its cost. State-of-the-art studies do indeed exist. A system, an exoskeletal control, which was based on EMI, utilizing EEG and SEMG, was indeed examined by Vellore in 2015 for the purposes of enabling neurogate rehabilitation with hybrid robotic system, as cited by number 1 in the paper based on which this presentation is made. In 2019, a single leg knee joint assistance robot, an exoskeleton that is, tested over stair ascending, descending, and general walking conditions of operation was examined by Moon et al., while Liu et al. Examined the development of an EMG-controlled knee exoskeleton to enable the assistance of stroke patients during rehabilitation. Chen et al. In 2021 explored the development of a microcontroller-based multi-layered closed-loop control system to assist ambulatory individuals with cerebral palsy, while in 2020, Zhang et al. Proposed the complete elimination of using conventional drives to actuate joints using shape memory alloys, SMA, instead. So in the face of all the study and additional studies as part of our research, we found that the body of studies which examine the feasibility of alternative perception strategies, especially computer vision, for economical exoskeletal actuation approaches and applications was indeed quite restricted in span. The amount of work, which also examines the choice of actuators, comparing their performance parameters and comparing the smoothness levels and economy of implementation is also not that extensive. In view of this cause, the investigation into the plausibility of adopting awareness and integrating this with real-time environmental perception within a singular system economically, which parallelly enables actuation extrinsically of the knee joint, is indeed in need of drastic intensification. So, of course, the prime system objectives for such a system must serve as a developmental motivation for us. So we've diverted our effort, we've established our understanding and distributed our efforts over a 5-fold understanding, which spans obstacle detection, wherein varieties of obstacles of different dimensions must be measured and detected and dimensioned. Thereafter, real-time feedback, proportional actuation based on the category, based on the dimensions of the obstacle again. And it being a product which is aimed at the consumer market, must indeed feature user control, modularity, scalability, adaptability, and most importantly, vitally, variability. In view of these constraints, challenges, and for the purposes of addressing this problem, of providing a low-cost actuation solution to visually impaired and differently abled individuals as well from the knee joint. At the knee joint, we propose a Lumina gate-based solution, which is implemented by a prototype, which focuses on empowering vision and thereby enabling stride. The constituents of the system include connecting wires for the camera and for the LiDAR unit, a computer processing system, an exoskeletal frame with appropriate fasteners, a servo motor, and a waist strap onto which this fusion of camera LiDAR unit is mounted. Once again, the same system but from a different viewpoint. The image to the left again divides the entire mechanical framework into a torso end and a calf end, with the torso end featuring a lead connection base, servo motor assembly, and knee joint foam padding for comfort, with a microcontroller base mount onto which the MCU is mounted, while the lower frame section features a calf end and ankle foam padding as well. At the same time, the image to the right, top right, shows how the system is connected in its entirety, with the waist strap featuring the consolidated unit and the appropriate connections made to the computer system on which the computer vision code is run. It may be important to note that the computer vision code was developed using Python and communication performed via the serial ports and pi-serial communication protocols. The system working is also presented here with a real-time video feed at 30 frames per second is captured and every frame is individually extracted. Frame pre-processing is carried out with regions of interest being obtained and followed by image processing approaches whereby RGB input frames are converted to the HSV color space, and the isolation of these objects of interest, the obstacles that is in turn carried out via the process of image segmentation. Image contours are detected when bounding rectangles are wrapped around the objects which are to be dimensioned. The data from LiDAR sensors serve as the distance data, which again serves as the fundamental input to the computer system as to what is the distance between the user and the nearest obstacle. The camera feeds in the input image on which the contour overlay is carried out and dimensioning is subsequently performed. Actuation logic is thereby carried out, and mechanical support structure, which was developed exclusively for this prototype system version 1.0, was also performed. It acts as a load-bearing support structure with the focus of ease of assembly and disassembly also. The assembly constitutes also includes a modular design, or rather focuses on a modular design with a specifically designed frame housing all the electrical components and processing hardware. We've tested the system and we've also presented the results here with. A quick overview of the operational schematic of the prototype. An obstacle in the path of height y is detected by the camera unit around which a contour is wrapped. The LiDAR sensor measures the distance between the user and this obstacle in the value x. These two units send the data as a whole to the control, the central processing unit. The CPU thereafter relays based on threshold commands. Is the object of sufficient dimension? Is the object sufficiently far away or close to the user? Based on the thresholding and internal decision parameters, the processing system relays an appropriate actuation command to the microcontroller unit, which thereafter signals an appropriate actuation command to the servo drive, which drives the lower half of the mechanical frame, to which the entire leg has been mounted. Now, this can be seen. The way in which it's been mounted onto the leg can be observed in the image to the right. An overview of the costing has also been presented. Contemporary developments range anywhere from $20,000 to $120,000, at least in development. But our proposed system aims at presenting a second version for just under $500 at the very least. At the same time, this is something we try our level best towards achieving. The second table highlights a breakdown of the costing of the current prototype, which we have presented in the images in this presentation and in the paper also. The net material cost and the DMC does not exceed 6,000 rupees, or in other words, fall just under $70. As part of the evaluation of our prototype, we've examined the structural integrity, ergonomics, processing performance, and detection capabilities of the system, and we were able to conclude that yes, for such a cost, we were indeed able to achieve the functionality of an incredibly expensive system, but again, with a fraction of its overall economy in cost. The image processing performance was found to be commendable. There was indeed real-time perception, strong capacity of detecting objects in the face of image noise, the varieties of lighting conditions, Even the object dimensioning was found to fall within 10 to 20% of an error when compared to the actual object dimensions. So the fusion approach, fusing camera and LiDAR data, was indeed effective. The sensing of depth by the LiDAR sensor was indeed carried out with minimal measurement latency. The analysis of the system's cost was also found to be incredibly interesting, since we were able to achieve contemporary exoskeleton functionalities under, I just say, 2.5% or less of the average cost of other consumer exoskeletons. Of course, at the same time, nominal actuator jitter during rest implies a slight departure from ideal control, which would be addressed through signal condition provisions in the actuation code and perception program macro in the subsequent iterations of the system. So, as part of the results, we developed a functional prototype of a low-cost exoskeletal system. We proved that the integration of camera and LiDAR data to achieve distance measurement, obstacle dimensioning, and proportional actuation could be achieved for a very low cost, and at the same time promoting use of ease of use, and at the same time promoting user comfort and convenience as well. This is what the conclusion states. We presented a prototype and we've developed this prototype and presented the important aspects of this in this particular presentation and in our paper. A cost analysis has been presented also, and the affordability of our system has been established time and again. In this particular picture, an overview of the exoskeleton can be seen with the associated subsystems. As part of our scope, since this particular study is a preliminary one, we would of course ensure that different threshold and distances of separation between LiDAR and the obstacle does render the same object dimensions and at the same time provides the same values with minimal measurement latency. The goal would be to develop an exoskeleton which closely resembles a human knee joint and leg, and at the same time also considers real-world conditions such as shocks, jerks, and improper fastening. Thank you. With this, I conclude my presentation.